All right, so let's talk about bases now. We can treat bases the same way. How do you tell if they're strong or weak? Well, strong bases are simply the group 1A and 2A hydroxides. Those are the easy ones to remember. So any group 1A or group 2A hydroxide is a strong base. Everything else is going to be considered a weak base. Okay, so sodium hydroxide, calcium hydroxide are strong bases. To find the pH of a base, pretty much the same thing as pH of an acid, although we have to go a slightly different route. Remember that strong bases completely dissociate into whatever the metal ion is and the hydroxide ion. Okay, so if we have 5.0 times 10 to the minus 2 molar sodium hydroxide, that's the concentration of hydroxide ions. We can find the OH, the H plus concentration by dividing Kw, 1.0 times 10 to the minus 14, by the hydroxide ion concentration. That'll give us H plus. Take the negative log of that and you get your pH. Remember, pHs of bases should be above 7. That's how you can sort of check to see if you're on the right track. There's another way to do this. There's another way to get the pH rather than the way that I just showed you. Think about it and see if you can figure it out. Okay. What about if it's a calcium hydroxide solution? Notice that calcium hydroxide has 2 moles of OH minus per mole of CaOH2. Think about that. How would that affect your calculation? Okay. For weak bases, they don't contain hydroxide. They do accept H plus to make OH minus from water, right? So we can calculate still the concentration of OH minus, and then we can from there calculate the concentration of H plus and find the pH, right? Bases usually have an unshared pair of electrons. We'll see later on that that's the Lewis, part of the Lewis definition for bases, okay? And that the base, that extra pair, can form a bond with the H plus. It's a covalent bond between the H plus, and that's sort of how the H plus attaches to it. That's how it accepts the proton. So for example, with ammonia can take an H plus from water because it has that nice lone pair of electrons. The H plus will attach to it to form NH4 plus, the ammonium ion, and hydroxide ions. Okay, we do have Kb values, which is the same as Ka, only it's for bases. Okay, it's the reaction of base with water to form a conjugate acid and hydroxide. For example, our base is B. We react it with water. It takes a proton from water, becomes BH plus and OH minus. That means our Kb expression will be concentration of products, BH plus, OH minus, over the concentration of the initial base, the weak base, B. Water, of course, does not show up because water is a pure liquid and they don't show up in equilibrium expressions. So no different for bases than it is for acids. Okay. If we want to find the pH of a weak base, we're going to use an ice table again. We're going to use our Kb expression. We're going to solve for X. It's the same type of problem. So here's an example. 15 molar NH3. 15 molar, that's pretty high. Okay. Kb value for NH3 is 1.8 times 10 to the minus 5. It's a small value of Kb, so this is a weak base. It's not going to accept too many protons. It would rather be NH3 than NH4 plus. Okay, so NH3 is going to create more OH minus than the water will because there's more of them to accept protons. That's what the Kb value is. Kb value is much bigger than Kw, which means it's more of a base than water is. Okay, so our ice table is set up exactly the same as it always is. We don't care about the water because it doesn't show up in our equilibrium expression. The initial concentration of NH3 is 15 molar, 0 and 0 for NH4 plus and OH minus. It's minus X for the base, plus X, the usual. Okay. Plug that into our Kb expression. We can make the approximation, again, because we're going to assume that X is very small compared to 15. 15 is huge. X is 0.016, obviously less than 5%. We can do the check, right, but 0.11% we're talking about. So X is my hydroxide concentration. I need the H plus concentration to find the pH, so I divide the hydroxide concentration into 1.0 times 10 to the minus 14 to get the H plus concentration, take the negative log, as usual. Okay, pH is 12.20. Okay, here's another example. I want you to write this down, stop the video, and try it. Okay, this time I've given you the pH. I want you to find Kb. It's going backwards. Okay, got it? See how you did. Well, first, what's the chemical reaction? Codeine plus water goes to protonated codeine plus hydroxide. First, we need to find the OH concentration, OH minus concentration, because we have the pH, so we don't need to do that. We can use that information to find the hydroxide concentration. Remember, I can go, instead of just taking the pH and taking the anti-log and finding the H plus concentration, I can go the other way too. I can say, well, POH plus pH is 14, so POH is 14 minus the pH, which is 4.05, and then take the anti-log of that. That gives me my hydroxide concentration, 8.9 times 10 to the minus fifth. So when I create my ice table then, my initial concentration of codeine is there. There's nothing, no protonated, no conjugate acid, no hydroxide at the beginning. The change is still, this is a monoprotic exchange, one hydrogen ion exchange, so it's minus X plus X plus X. That gives me 5.0 times 10 to the minus 3 minus X, and X and X, but we know what X is. We know the hydroxide ion concentration. We were just calculated that, so I can plug that into my expression now, and I can find my Kb is 1.6 times 10 to the minus 6. So we did an example of that in a previous video with a weak acid. It's the same thing. Polyprotic acids. A polyprotic acid means that it contains more than one ionizable hydrogen. Okay? The hydrogens pop off one at a time. So first, all of the molecules have to give up their first H plus before they can give up their second H plus. Carbonic acid, H2CO3, has two dissociations. First to H plus and HCO3 minus, that has a Ka value of 4.3 times 10 to the minus 7th. The second is HCO3 minus to H plus and CO3 2 minus. That has a Ka2 of 5.6 times 10 to the minus 11. The second ionization of polyprotic acid is always going to be much less than the first. The first one's always stronger, okay? And if there's a third one, that's even less. So that's typical, okay? Why do you suppose that is? Think about it. Why would the first dissociation for polyprotic acid be much more complete than the second and third? Well, think about what you're making each time. You're making a solution that's becoming more negative. It's not going to want to give up another proton. You're already saturating the water with protons. So you're creating an equilibrium position that you don't want to add more protons for. Some important ones that we use all the time in lab, phosphoric acid, okay? Only the first step, the first dissociation, creates an important amount of H+. The next two dissociations, not really. Sulfuric acid, this is one that most people don't think about. We consider H2SO4 a strong acid, but it's only the first step that's strong. All of the H2SO4 goes to H+ and HSO4-. The HSO4- is a weak acid, and it can dissociate a little bit, but probably not a whole lot because you've already got a ton of H+ in solution from the first dissociation. Okay, but we need to consider that when we're doing calculations, pH calculations, etc. So 1 times 10 to the minus 2 molar sulfuric acid solution, we want to find the pH. So we've got our important species are H+, HSO4, H2O. The H+ concentration for the first dissociation is going to be equal to the concentration of the acid because it's strong. We can plug that in then as our initial concentration of H+, because it's going to be there. The minute you put a sulfuric acid into water, it dissociates that first dissociation. It's there, okay? So our initial concentration then of, we're looking at the second dissociation to figure this out, okay? So HSO4 will be 1.0 times 10 to the minus 2. Why is it the same as the initial concentration of sulfuric acid? Because all the sulfuric acid molecules dissociated. So you have the same number of HSO4-. And the H+ concentration is the same, okay? A little bit of HSO4 is going to go down, minus X. A little bit of SO4 2-, and H+ will be created a little bit. So that gives me new equilibrium situations, okay, new equilibrium positions. I can put those in. I get X times X plus 1 times 10 to the minus 2 over 1 times 10 to the minus 2 minus X. We're going to assume that the amount of X that's being added is pretty small. But we can't necessarily make that approximation because 1.0 times 10 to the minus 2 is for a small number to begin with. So I'm going to just solve using algebra, right? I'm going to come up with X is equal to 4.5 times 10 to the minus third. The H+ concentration is 1 times 10 to the minus 2 plus 4.5 times 10 to the minus 3, which is what we just calculated. X is the additional, which is 0.014. pH is the negative log of that, and 1.84. So I didn't make the approximation here because the value of X was pretty close. I thought it was going to be pretty close, not quite 5% or less than 5% of the initial concentration here, because the initial concentration is pretty small. So you have to kind of judge it a little bit. If you had made the approximation here, you would have to check it, and you would notice that it was greater than 5%, so you'd have to go back and do it this way anyway. Okay, so calculations for bases, pretty much the same calculations for polyprotic acids. You just have to consider what happens with the first dissociation, second dissociation, if there's a third one, which one figures in the most in terms of producing H+. It's like a mixture of acids. It's dealt with the same way.